This is a production of Cornell University.
So today I'm here to talk to you about, I tried to focus on one aspect, and I'm going to mostly tell this story about the work that I've been doing with culinary herb production in controlled environments. And so why culinary herbs? Well, first, there's going to be a low barrier to entry compared to your high wire crops like your cucumbers and tomatoes, and that's going to be related to those floriculture growers who are maybe interested in retrofitting their facilities, trying to get into food crops, or for new food crop producers who are learning how to grow in a controlled environment. When you've got a 4-week crop time, you can afford to make more mistakes and it's not quite as costly. In addition, that short-term production cycle is also useful for patching into a traditional greenhouse crop program. It can serve as a gap crop when you're looking from maybe poinsettias through to spring, that holiday season. It can serve a purpose during that time of the year. And also it's increasing in popularity as people are getting more interested in food, cooking, and food crops. Culinary herbs come along with that. But a lot of it also has to do with the value of the crop itself. And it's the third most valuable controlled environment agriculture crop behind tomatoes and cucumbers. And if you just look at some trends from 1998 to 2014, you're going from 192 producers producing around 31 million up to over 2,000 producers, and you're just south of 800 million for a value in that crop. And so it is a high value horticultural crop. So that's increasing the relevance of this crop, not only among consumers, but mostly for commercial producers. They see this as a potential revenue stream. When you think about what sort of resources you have, or what sort of resources commercial growers have to support greenhouse crop production, what do they have? So Neil mentioned my academic background, but before I went back to graduate schools, I was actually a commercial grower. I'm still a grower at heart. I started out with a two-way split, and I asked for an extension appointment because I wanted to work with growers. For me, it's all about the crops, and it's all about producing these plants. And so I like these resources. Like last night, Kendra, we were talking about the resources available to growers. So what sort of resources do you have? You know, we've got books on poinsettias. We've got books on bulbs. We have tomes of information on certain crops, but what is there for culinary herb production? So when you go and Google search for hydroponic herbs, the results that you get kicked back as an untenured professor with Iowa State University property, you don't get a whole lot on culinary herbs. So when you sit back and you think about how can you support commercial producers, what sort of information do they need to sufficiently grow a crop profitably and of high enough quality, there's a number of things from cultivars all the way to marketing that need attention, that need good peer-reviewed science to provide sound data for them to make their decisions off of. Those decisions that affect their livelihood when we're looking at heating costs or crop cycles. I don't specialize in all of these areas. What I did is I sort of picked those areas that I'm most interested in. And today I'm going to be talking about cultivar selection, production systems, some nutrient solution work, and then light and temperature. Those were the areas that I felt I had the strongest value to bring from my background in research and from my own interest as a scientist. So this is where I just wanted to start to generate data that would support the commercial production of culinary herbs. So when we start out in cultivar selection, for some species, such as basil, there's dozens of cultivars that are available. For other species of culinary herbs, there's going to be relatively few cultivars that are available to choose from. And Jonathan, early today, we were talking about strawberry production, and you were talking about how there needs to be some breeding for cultivars for the greenhouse. And it's the same thing with herbs. There needs to be some targeted breeding for controlled environment crop production, but there's not. And so as a result, we need to utilize those genetics that are existing on the marketplace and figure out what sort of genetics bred for the field work well in the greenhouse. So the first CEA project I did on hydroponic herbs was with a master's student, Kelly Walters, who's just getting ready to finish up a PhD at Michigan State. But we started out by looking at 35 different basil cultivars. And we looked at 2 different production systems, but I'm just going to focus right now on the cultivars. And so we got these 35 cultivars across a number of different basil classes. Of course, we've got the sweet basil, but we also had the purple or the opal basils, large leaf basils, cinnamon, Thai, bush, lemon, and holy basil. So we tried to get a wide variety of basil cultivars to evaluate their productivity in a controlled environment. And here we have just a selection of those results, okay? So we've got one cultivar from each of the different classes, and we've got the fresh mass, the leaf index, and the branch number. And then below here, you can see images of the different leaves from these cultivars. And so this is just meant to demonstrate the variability among the different types of basil that we have when it comes to the amount of productivity and the size of the leaves of these plants. But let's focus on sweet basil. So here we've got over a dozen sweet basil cultivars, from aroma to superbo and sweet basil. We've got the fresh mass and the height and the leaf index and the branch number. But really, horticulture sells the most valuable packaged water. That's really what we sell, is we sell packaged water. We sell fresh mass. And so that's going to be something that's going to be probably one of the most important things to commercial producers. And when you look at the variation in cultivars, Emily producing 15 grams in one plant after 3 weeks of finishing versus Italian largeleaf producing over 50 grams. That's over 3 times the increase in yield, just from depending on what seed you sow. And this example, I actually got to use in Iowa. I had a commercial grower that they grow tomatoes, but they also grow basil. I think they want to be a commercial bruschetta producer. But they were talking about their yields, and I asked them what they were getting. I said, well, what cultivar are you growing? He said, well, we grow Emily. And so this is an example where I said, well, there's a number of other cultivars that you don't need to change anything in your production system. You just need to change the genetics that you're selecting, and you're going to be able to have a pretty dramatic impact on your yield. You know, this is a relatively straightforward and simple experiment or trial, but the value of having data, again, to support this decision-making is important.
Chris, what is leaf index?
Leaf index is a proxy for leaf area. And the reason we measured leaf index is if you had those tasty little lettuce wraps at P.F. Chang's, where you put the ground chicken, sometimes you can make these specialty things in large leaves. And so we're trying to measure the leaf size, or a quick measurement, for more specialty uses of leaf index.
Okay, so the bigger the number,
Yeah, the larger the leaf. It was just it was sparing Kelly running them all through a leaf area meter. So again, don't underestimate the importance of cultivar selection. This is the simplest way to improve your yield. Now, you do have lower yielding cultivars that we had in this study. And those are going to be acceptable for growers if they can get a premium on that price. So for example, some of the lower yielding, like the citrus flavored basils, the lemons, the limes, they're lower yielding, but there's a higher premium on those prices, or some of the Thai basils. So those lower yielding cultivars can be acceptable, assuming you get the price back on the lower productivity. So just like you have a choice of cultivars to select, what are you going to grow them in? Now, there are a number of suitable systems for hydroponic herb production. The 2 most popular are going to be recirculating water culture systems, like the NFT system, nutrient film technique, or then the raft or the deep flow technique system. I call that the DFT system. And here we have a commercial shot. This is actually a greenhouse that was converting from ornamental production with their Dutch trays into NFT lettuce production. And this is Green City Growers outside of Cleveland, Ohio. This is one of their basil ponds, the raft, or that deep flow technique. And again, these are the 2 systems that are most well suited to leafy crop production. So we wanted to, again, compare these 2 different systems. And so we had our own DFT systems and our own NFT systems. These were smaller systems, so we could replicate them and have 10 of each independently. This is also what we grew all those cultivars in. And there are a few differences. Our DFT, you'll notice that it's elevated. Because I wanted to make a really sound scientific comparison, I wanted to have the exact same light intensity at plant height. And so we brought our DFTs up off the ground so they would be at the same height as the NFT, so we didn't have any confounding factors. We also had a heater chiller that was keeping the water temperature the same. DFTs can sometimes be warmer because they'll hold a larger mass of water that'll hold that heat in them. So we tried to correct for those potentially confounding variables to compare these systems. And when we looked at the effect of cultivar, again, those 35 cultivars, and systems, and then the interaction of cultivar by system, these are the results that we got. And the data that I just showed you before, it's inherent that we would have variations in cultivars. That's why we have all those different types. But the lack of an effective system, and more interestingly, or more importantly, the lack of a cultivar by system interaction means that growers have flexibility in which system they can select. Now, there are differences between NFT systems and DFT systems. Again, you get comparable growth, but there are some differences as far as the ease of maintenance. I look at NFTs, and being from Minnesota, the land of 10,000 lakes, NFTs are the land of hundreds of potential leaks with all the tubing that are on them. So there's a little bit more plumbing involved in them, but there's some ease as far as lifting up the channels and bringing them to harvest and sanitize. Rafts, those are really nice because, again, you can lift up that raft for a harvest. And if you have a power outage and you have a lack of circulation, hopefully they're just going to be floating on top of that solution. But you also have to think of the ergonomics. Rafts aren't always going to be elevated to waist height. People are going to be bending over and working on those. So you have to think of the ergonomics and the workflow and think of the people who are going to be working these systems. So your decisions don't have to be based on plant productivity or plant biology. You can base them off of the economics of the system to install and maintain. Okay, so that was...
Chris, how deep is the pond in the DFT system?
In this one, we were at about an 8-inch depth. And commonly, I think if I would say the range is from 4 to 6 inches up to about 12 inches. Bill, do you have a question? Okay, that's on your hand. And if you have questions at any time, as a faculty member, I have the gift of gab and I can talk at length, but I'm more than happy to answer questions while we go, if it's a more organic approach to answering what questions you have. So please don't be shy. So now that we've looked at systems and we've looked at cultivars, I wanted to move on to nutrient solution electrical conductivity. So the EC of a nutrient solution measures the total amount of fertilizer salts or ions in the concentration. That's how we monitor fertilizers in hydroponic systems. We're not necessarily measuring specific nutrients in their concentrations. Rather, we're measuring that over total all concentration. And along with pH, this is going to be something that we measure and that we monitor and that we change throughout production and try and keep consistent to keep a consistent crop quality. But again, the question is, what sort of an electrical conductivity do you have to maintain in these herb production systems? And a lot of times an herb system is going to be a polyculture. When we look at a tomato greenhouse, you're usually growing just tomatoes, or a cucumber greenhouse, just cucumbers. If you're in a lettuce greenhouse, it's normally going to be just lettuce, maybe some red and some green lettuce. But when you have an herb production program, that's going to be a polyculture where you have to grow a number of different species because of course, you're going to grow basil. That accounts for the vast majority of culinary herb sales. But you're also going to have to grow other species along with that because people don't want to go to a basil producer and a thyme producer and the rosemary producer. You have to produce everything. So in those polycultures, what sort of electrical conductivity can you maintain your systems at to maintain the growth and health of the crops that you're growing? So again, for this system, or for this experiment, we used NFT systems. And here you can see the range. We used 5 nutrient solution electrical conductivities from 0.5 to 4.0. And when I'm doing these dose responses, I like to try and go from suboptimal to nuclear, so to speak. And that's a pretty reasonable range as far as electrical conductivities for commercial production. But then we also wanted to conduct them under 2 different lighting environments. The greenhouse is dynamic with respect to light. You probably heard some of that from Dr. Mattson in his lab. Light is what drives a lot of the productivity in a greenhouse. And how do you have to adjust the nutrient solution across different lighting environments? And so we ran this experiment under 2 different daily light intervals. One was about 7 moles per day. And in Iowa, that would be what you get around in a greenhouse in January. Then the other DLI that we ran it under was about 16 moles per day, and that's a pretty good day in April. It also could simulate a winter greenhouse in Iowa with no light, and perhaps a winter greenhouse with supplemental lighting. Again, we'll talk more about the yield and growth of herbs under light later, but that's a main driver of productivity is the photosynthetic light. So when we look at basil grown under 0.5 to 4.0 under a low DLI of around 7 moles per day or a high DLI of around 16 moles per day, even though these look a little bit smaller, when we look after multiple replications and we run regression analyses, electrical conductivity doesn't affect the fresh mass of basil. Light does. So we had over twice the yield under that high daily light integral as we did under that low daily light integral. So photosynthetic light had a large impact on the productivity of that crop. But electrical conductivity didn't. And this is something that for me was pretty interesting, because a lot of times I'll talk to a grower and they'll say, I'm trying to push my crop, so I'm increasing the fertilizer. But that's not necessarily a strategy that they can use to increase the yield of their culinary herbs. What we did is subsequently looked at the tissue nutrient analysis of that crop, trying to figure out what the concentration of these nutrients were. Because in addition to producing biomass, we also want to have healthy appearing biomass. And the appearance of a crop is going to be largely influenced by tissue nutrient concentrations. You know, if you have a plant that is deficient in nitrogen, you'll have chlorotic leaves. If you have deficient magnesium or iron in basil, you'll have interveinal chlorosis. And that's going to render that crop less marketable. So when we look under here, the open symbols are the high daily light integral, and the closed symbols are a low daily light integral. And you can see that the tissue nitrogen concentration is increasing with increasing nutrient solution EC. And that makes sense. We've got a stronger nutrient solution. They've got greater tissue nutrient concentrations. But when you look at the sufficiency range for sweet basil, we're trying to achieve 4 to 6% nitrogen in the leaves. And you can see that under that 0.5 millisiemens electrical conductivity, we were above that. We were well within that sufficiency range. And we didn't get any super optimal ranges, even though we were starting to get close to that upper limit. But we were across electrical conductivities, we had healthy appearing tissue. And if you look at across the nutrients, macro and micronutrients, generally speaking, the concentrations increase with electrical conductivity. Now, the concentration of calcium and magnesium decreased with electrical conductivity. And there's two reasons why you might see a reduction in calcium or magnesium. One, it might be a dilution effect. As something gets bigger, even the concentration might increase, the total content, or the content might be increasing as well, the concentration could go down. But we didn't have an increase in mass. Rather, what we think happened is we adjust our nutrient solutions with potassium hydroxide. So we've got positively charged potassium, we've got positively charged calcium, and positively charged magnesium. Those three nutrients often interact in nutrient solutions. So by having to make our additions of base to raise the pH and keep it within a target range, we're increasing the potassium concentration that likely caused competition for calcium and magnesium uptake. You know, calcium and magnesium have an antagonistic relationship, but so do so does potassium as well with those nutrients. So again, we were at or above sufficiency ranges for all our tissue nutrient concentrations. Now, again, we work in polycultures and herbs, so I ran the same experiment. We've got cilantro, high DLI and low DLI, dill, high DLI, low DLI. We've also done this with flatleaf parsley. And now we've been able to publish all the data, and it was the same for these other species, just as it was for the three different basil species that we use. We saw the same effect, that we didn't increase yield or saw no promotion of growth with increasing electrical conductivity in the nutrient solution. It was primarily an effect of light. So the practical implications is that as long as you're adjusting your nutrient solution EC regularly, that's why I've got a shot of this doser here, you can run a low electrical conductivity and you'll be just fine. Now, if you're not adjusting your nutrient solutions regularly, if you're doing it maybe say a smaller operation 3 times a week, or something more periodic, you may want to run a higher electrical conductivity to account for the depletion in between additions. But again, these herbs are very nutrient use efficient as far as their uptake and their growth in response to nutrients. And if you think about a lot of these herbs in their native environments, they come from relatively less than optimal growing environments, so they likely have evolved to have efficient use of those mineral nutrients that are available. Okay, so I've talked about cultivars, systems, and nutrition. Now we're going to move into temperature and light. Light's going to influence the growth, that irreversible increase in mass. Temperature primarily increases or influences the rate of development Being that I'm a Minnesotan and it's so cold up there, I'd like to think that's why I'm so short. It was just an effective temperature. But we can really use air temperature and its effect on crop development to schedule and predict yields. Again, this is going to vary among species. So when you look into the literature, if you go into the USDA Virtual Grower, they've got a program called Flowers on Time now, and they've got dozens and dozens and dozens of floriculture species that have the time to flower based on air temperature, this model that you can use, and it's a great predictive tool. But again, where is that for the herbs? And so that's what I want to set out to do. When we look at air temperature, here we have the common response. This is just a generic curve. When we've got our rate of growth or rate of development on our y-axis, and we've got air temperature down here, this represents the common response of plants to air temperature. That base temperature, the temperature at or below which plant development stops. We've got our optimum temperature, which is that temperature that results in the maximum rate of development. And then we've got, our optimum temperature at that maximum rate of development, and then our maximum temperature, which is the temperature at or above which plant development stops. Now, between the base temperature and the optimal temperature, we have a linear range. And this is great because linear ranges are where we are many times in greenhouse temperatures. We're often within that linear range. The other benefit is that a linear model, y equals mx plus b, is relatively easy to use as far as a predictive tool for growth and development. So I spent a couple of years modeling the growth of herbs in response to air temperatures. We had 5 temperatures that we used, 11 to 35 degrees Celsius, and we had 16 species and cultivars, including 4 basil species, 2 cilantro cultivars, and then a host of other culinary herbs. Thank you to the students who watered these plants, particularly those that were in the 35C chamber. But right now I'm getting around to writing up the rest of this data because I don't want it to die in vain because of the amount of maintenance that this took to make this experiment go. But this is what we ended up seeing. You know, we got the data, leaf unfolding, fresh mass, dry mass, and height for all of these species. And you can see that the response of this lemon basil pretty much follows that generic curve that I had, right? It's going to increase from the base temperature, which is just a little bit below 11, up until that optimal, which is right around 30, after which point it's going to decrease. So lemon basil, as well as the 3 other basil species we had, is a cold sensitive, warm growing crop. Warm growing because it has a high optimal temperature. Alternatively, basil and flatleaf parsley, you can see that it's got a more moderate optimal temperature, should be grown a little bit cooler. You can also see that even though it was growing slowly in those cold temperatures, the growth was greater and it's more tolerant of those cold temperatures. So again, these photos complement that curve, but how we use this data, here we have the fresh mass accumulation rate for dill. So it's the grams per day of fresh mass. Using this, we can solve for an optimum right at 23C. Then what we do is we exclude those super optimal temperatures, and then we put together that nice linear model. We can calculate the base temperature being right at 8 degrees Celsius. And then we can use the linear model to predict growth. So just to show you for an example, if we were to use our data on sweet basil, we can predict basil harvest. We generally plant right around a 1 gram seedling. That's the shoot fresh mass of the seedlings we're producing, usually about 2 weeks old. And we're trying to get at least 21.3 grams, which would be 3/4 ounce. I like to envision every basil shoot being the shoot that will fill that 3/4 ounce clamshell packaging, which is the most widely sold herb. So again, here we have that response of sweet basil. Looks a lot like lemon basil. High optimal temperature, sensitive to cold. And here's our linear range. So we take that curve. We exclude those temperatures that are super optimal. We've got our basil fresh mass gain, fresh grams per day, equals 0.087 times the air temp minus the intercept, 0.985. And using this model, if we were to grow at 18, 20, or 22 degrees, these would be our fresh mass rates, meaning we would achieve that 3/4 ounce size, that 21.3 gram shoot at 35 days, 27 days, or 22 days as we grow from 18 to 22. Okay, so this is a tool that growers can use, again, these linear models, to predict the growth of basil and estimate harvest, or if they want to make changes in their energy use, changes in their air temperature, they can estimate the impact that this is going to have on the crop time for their herb crops. So again, the herb responses to air temperature vary, both in the magnitude of change as well as their base temperature and their optimal temperature. These predictive models are going to be useful for predicting changes as well as informing change that you're trying to do. You can also group your crops by temperature. If you've got a large enough production facility and you have multiple bays, you could have a warmer greenhouse for basil to try and finish those crops more quickly and have more turns. But then you can have a slightly moderate greenhouse for things like parsley and dill, chamomile, these other herbs. So you can start to group crops based on their actual requirements. Okay, so we just talked about development. I want to talk a little bit more about light. And this is really where a lot of my work has been focused. Part of that comes from my background at the University of Minnesota. I worked on light, as well as at Purdue University. I also worked on light. It also has to do with the location that I'm in. Being in a northern latitude in the United States, light can often be one of the more limiting factors in greenhouse crop production. And again, temperature affects development, but light really affects the mass of plants. And that's what commercial producers are selling. They're selling mass. If we were an ornamental grower, we're selling units that look aesthetically pleasing. You know, an appealing looking container, a nice looking flat. But with food crops, we're selling mass. In ornamental crops, we often have to try and justify the cost of lighting using supplemental light because it's got to have a translation in the quality of the crop that will get a higher premium. But this value proposition is much easier in food crops because we sell mass. Primarily, we're interested in the quantity of photosynthetic light. Now, I'm going to talk a little bit more about light quality and spectrum, but it's the photosynthetic light and the quantity of it that's going to dictate the amount of mass that's produced. Day length and photo period it can be a concern, especially when we're trying to inhibit flowering of many of our culinary herbs or induce flowering of some of the recreational herbs. But we're primarily looking at the quantity of light. So again, here we have, I did some work, or actually my PhD student started his PhD on light and herbs, screening the responses and modeling growth in response to daily light integral. Daily light integral is the cumulative amount of photosynthetic light over the course of a day. And we tried to use a range of DLIs. We went as low as about 2 moles per day, up to approximately 20 moles per day. Now, for those of you thinking like you wouldn't have 2 moles in a greenhouse, I encourage you to come ice fishing this winter in Minnesota, and you'll absolutely have 2 mole days inside of the greenhouse. It's very possible. We didn't go above 20 moles because above 20 moles, even though light could be promoting growth for some of these species, in a greenhouse, that's when you're going to start to reduce light for thermal management and temperature management. So we tried to use that range of DLIs that are most useful for managing photosynthetic light. And we focused on 8 different species of herbs, from basil to thyme. And as is probably no surprise, the yield of herbs increases with increasing daily light integral. Again, here we've got the 8 species: basil, cilantro, parsley, dill, mint, sage, thyme, and oregano. And for 5 out of the 8 species, we had a linear increase in yield in response to daily light integral. Okay? For 3 of the species, we did start to get to a supraoptimal point. Okay, so we started to get to a point where they were getting saturated with light, and yields started to plateau or even diminish at some point. So even though yield does increase for all these species, it doesn't increase to the same magnitude. Oh, sorry, let me go back actually. So since we reached those optimal with mint, parsley, and sage, we can classify these, much like we're classifying herbs with their temperature responses as cool growing, moderate growing, or warm growing species. We can classify herbs based on their lighting requirements. So none of the herbs that we found were grown under or would be classified as low light plants, requiring 5 to 10 moles per day. 3 of the species we consider moderate light plants, requiring between 10 to 20 moles per day. The remaining 5 species, they're either going to be high or very high light plants. We can't classify them more precisely because we didn't reach that optimal light level. So they're going to be one of those 2, which is going to be, again, a high light crop, especially for a greenhouse. Like I was saying, increasing light increases the yield, but the magnitude of change varies across the species. So let's take, for example, if we look at basil. Now, if we look at basil and we add, let's go from 8 moles to 12 moles of light, okay? And that we're adding 4 moles of light with supplemental HPS light. That's why I use the color coordinated yellow. We're gonna increase our yield by 40 grams, okay? Alternatively, if we add that same amount of supplemental light to the oregano crop that we're growing, we're still adding 4 moles of light, we're only increasing our yield by 6 grams. Same amount of light, same amount of energy input, but the amount of return on investment is gonna be much lower for oregano. So one of the ways that we wanted to try and convey this more simply is people aren't necessarily going to be growing under the same conditions that we have the same crop time. So we calculated the par productivity, which is a really fancy way of just distilling what's important from this. And par productivity is just the yield per mole of light. So you take your grams per plant and then you calculate out on a per meter squared basis what it is. Then you've got your total crop time per day. Then you've also got that average DLI in moles per meter squared per day. You cancel out the meters, cancel out the days, you divide the grams by the moles, and you get par productivity, grams per mole. Just gonna be one single value. And using this value, it reflects that example that I just showed you on the graphs itself. Basil, par productivity of 6.3 grams per mole. Oregano, par productivity of 0.4 grams per mole. Okay, so the reason that this is useful is if you're thinking about using supplemental light, you can look at which crops are going to bring you the most return as far as biomass back per photon provided. All the plants are going to respond well to additional lighting, but you have to think about that bill that's going to be paid at the end of the month. So again, the light requirements, herbs are going to be either moderate light requiring plants or high or very high light requiring plants. That par productivity varies widely. You're going to have things like oregano and thyme that are going to have relatively low output per unit of photosynthetic light in. So again, we can use these results to do some predictions on yield, as well as determine the effects of changing the DLI or adding supplemental light. Yes, sir?
What are the values of the different herbs different? A gram of oregano versus a gram of basil, is that the same? Or?
So generally, if we go back to that 3/4 ounce package, they're generally marketed at the same price point.
Okay.
So you'll see differences sometimes in like a lemongrass, because that's generally going to be imported and that will cost more. But generally, the clamshell pricing is uniform across that suite of products. Does that address your question? Cool. So now that I've talked about the importance of light, how are we going to increase light? And aside from going up and making sure you have clean glazing materials and minimizing the amount of hanging baskets overhead, that's just going to maximize transmission of light. The only way you can appreciably increase light is going to be to provide supplemental lighting. Traditionally, HPS lamps are going to be the most useful for increasing the DLI in a greenhouse, but there's increasing popularities in LED lights. Partially because of their energy efficiency, mostly because of their energy efficiency and their long luminous lifespan, how long they're going to last, but also they have narrow spectra. When we think about having those narrow spectra, we can start to think about doing cool things with plants. And I know a lot of people in Dr. Mattson's lab are doing cool things with specific wavelengths, blue, red, far red. We want to do the same thing with herbs. So we wanted to look at supplemental light and its effect on plants with a special reference to the proportion of blue light. So we took 3 supplemental light sources: high pressure sodium, an LED light with a low percentage of blue, 7%, the balance of 93% in red, and then LEDs with a high percentage of blue, 30% blue and 70% red. And then we wanted to look at the growth and flavor components of 3 herbs: basil, dill, and flatleaf parsley. And here we have, at the end of 3 weeks growth, we have our HPS plant, our LED with low blue, and our LED with high blue. And you can see that those plants grown under the LEDs are more compact. That's partially going to be because of the increased proportion of blue light, which usually results in more compact growth. It also might have to do with a little bit of a temperature effect on plants, with those HPS grown plants having a warmer temperature during the day and stretching a little bit. But we don't sell sizes in hydroponic plants. Again, we sell mass. And when we looked at the shoot fresh and dry mass, we had no significant difference in the shoot fresh and dry mass across our 3 lighting treatments. But what we did have is a significant difference in some of the polyphenolics that are in that basil. And you can see that in general, using the LEDs with the greater proportion of blue light enhanced the polyphenolic concentration in basil. Not all had statistical differences, but you can see that increasing trend. And the reason being is we love herbs because of their defense mechanism. Those compounds that are in herbs that flavor our dishes are what herbs normally use to respond to stresses and avoid herbivory. Blue light, 450 nanometers, is a high energy wavelength. And by using higher concentrations of blue light, that's going to enhance basically the stress response and be uploading or upregulating the synthesis of some of these compounds that, again, are attributed to the flavor in basil. We saw the same, a similar trend with dill, and we saw another similar trend with parsley. So this got us excited. We see there's a promotive effect of blue light on some of these flavor compounds. So we wanted to take it another step further and just see what even more blue light would do and look at the dose response of basil to blue light. So the follow-up experiment to this, we went inside of a growth chamber. I'm just gonna leave this photo of Will Ferrell up here a little bit longer while I explain this. Maybe that was me in a younger day. We went inside of a growth chamber and we went from 100% light to 100% blue light in 20% increments. And we grew Nufar basil in a deep flow-like system. So here we've got 0 blue, 100% red. And then we're slowly increasing the blue by 20% until we finally get to 100% blue. And then we did grow a chamber underneath white light as well. So after 3 weeks of growth, here are our basil plants, again, Nufar, going from 0 to 100% blue light. So earlier, what's your
white light source?
It was the Fluence white light. I can't remember what the exact spectrum is. I know I've got that in the manuscript and can share that with you. So I forget the proportion of blue light that it is, but it was Fluence's white LED. And the other array were Fluence arrays as well. In the previous slide, you saw those plants growing under LEDs were shorter and more compact, most likely due to the blue light. And you see that as we go from 0 to 80% blue light. Then all of a sudden you have that really tall plant, and I'll get to that in the next slide. And that's under 100% blue light. And then there's our white light grown plant. And again, here's the data showing the height decreasing with basil as you go from 0 to 80% blue, and then getting a lot taller underneath that 100% blue. And it wasn't a leaf unfolding effect. We had the same number of nodes on both of the plants. Rather, what happens is the phytochrome photoequilibria, when you're under 100% blue, changes, and it actually promotes stem elongation when you're under 100% blue. And when at first, as an advisor, you see this, it's like, well, blue light makes things shorter. My grad student must have done something wrong. But thankfully, he didn't. And this is also validated by other research. Ricardo Hernandez and Cherry Kubota demonstrated this with cucumber seedlings. And so, again, this is a common response when you're going under 100% blue light in a sole source lighting environment, not necessarily 100% blue in a greenhouse. Now, there is a bit of a yield penalty, though. As we go, we grew with higher proportions of blue light than we did in our previous experiment. And you can see that it's going to, leaf dry mass decreases as you increase that percentage of blue. The other problem is we're growing more stem proportionally. So here we have our leaf dry mass, our stem dry mass, and our root dry mass. And here we have the leaf mass ratio, stem mass ratio, and the root mass ratio. So the percentage of biomass in each of those organs. And you can see that even though there's no statistical effect and maybe a slight downward trend, the proportion of stem production increases under blue light. That's because we're getting less root production and less leaf production. But it is, again, growing proportionally more stem mass. And again, that's not the desirable part of basil. When we look at the gas exchange, you can see that stomatal conductance, intercellular CO2, and transpiration all increase with blue light. you also have an increase in photosynthesis up to 60%, after which there starts to be a slight decline. Now, you'll see that while photosynthesis was increasing, the total mass was decreasing. And that's because this was not done on whole canopy photosynthesis. This was done on a per leaf area, or this was a leaf photosynthesis. And if we go back and look at those basil shots, the basil have smaller leaves as the proportion of blue light is increasing. And so although you have a slight promotive effect of blue light up to a point on photosynthesis and then a reduction, your total photosynthetic area on the plant is decreasing underneath higher blue light because you have smaller foliage. So total canopy photosynthesis is decreasing. But when we look at, again, flavonoid concentrations in response to blue light, we see those same increases with increasing proportion of blue light. Again, we were working before between 7 and 30%, but here you can see going from 0 to 100%, we have a promotive effect of all those compounds in basil foliage. Again, with the potential to grow a more flavorful plant. So when we look at supplemental lighting, HPS and LEDs are comparable for improving yield. You need to consider things though like lamp density. You can use fewer HPS lamps than you do LEDs, so you might need to consider that. Increasing the blue light in spectra and narrow spectral lights may add value by enhancing flavor of basil, but it does come at a cost at a certain point. If you're using a high enough proportion, if you're trying to maximize some of the flavor compounds, you're actually going to have a diminished shoot fresh mass. The good thing is that you can actually grow basil on a very small center. You can grow it on a 3 or a 4-inch center if you're doing a short crop time. So you can potentially modify the amount of time that you or the amount of density of the basil in your growing area to make up for some of the yield penalties under that higher blue light. So to kind of wrap up this whirlwind of culinary herbs, select high-yielding cultivars. Select your system based on the cost of the system or operational functionality with your employees. Manage your nutrient solutions to minimize imbalances and solution exchanges. So make your EC management more about the concentration of absolute nutrients, and you can do that and stretch your nutrient solutions longer by using a lower EC more consistently. The temperature and the DLI models that we've developed can hopefully improve scheduling and predicting the yield of your crop. And then finally, select your supplemental light sources based on your goals. Are you trying to produce biomass, or are you trying to produce a more flavorful product? So I get to talk about all this, but I don't get to do much of the work at all. And so I would like to completely recognize Pete Lawler, our greenhouse manager, who makes sure everything is always running 7 days a week, 52 weeks a year. And then in particular, for these for the studies that I presented here today, Kelly Walters, Nick Flax, and Alex Litvin all played a really large hand in actually doing the work. And then we were supported by Farm Tech, Oasis, Johnny's, and JR Peters. So thanks to all of them for making all this work possible. Thank you so much for the invitation to come here. And with that, I'd like to take any questions that you might have about culinary herbs. Yes.
When you think about breeding targets, what is the most crucial thing? Is it necessarily going to be that mass because that's what they're getting, or is it going to be the polyphenolics or nutritional content?
Okay, so classic professor answer. It depends. You know, it depends on who you're growing for. If your basil is going into Cisco, into like a large agribusiness, then it's going to be yields. If you're targeting a more local market, co-ops, restaurants, then you absolutely could be looking for flavor over yield. But it does depend on your target market. I think I would like to say that we don't need to choose, and let's find a high yielding flavorful basil, because I think that's what people really want. You know, Genovese tastes great, Nufar holds up really well. So I would say it's probably the marriage of both of those, a flavorful but high yielding cultivar with a lot of leaf area, not a lot of stems.
Chris, would you ask Geneva if they have any questions?
Geneva, do you have any questions? Oh, have you conjuncted?
This is a new one, sensory analysis.
We have conducted sensory analyses with the Department of Food Science and Human Nutrition. We're still working to get those results back because that was a separate master's student and a separate PI who was taking our basil away from us in running the study. So we're still waiting to see if that translates, because we could be picking it up on really expensive equipment, but I'm not sure if people are actually sensing that. So it's a absolutely great question. Yeah.
Do you know if commercial like hydroponic basil growers, do they typically harvest the whole plant, or do they trim plants?
You see both. Just like I preferentially use micromole instead of foot candle and don't recognize foot candle, I'm a major fan of a one and done harvest. The reason being, when you think about pest management, I don't like having old tired plant material in a greenhouse. So I think it's best, even though you have an increased cost with planting, with substrate, I think about quick cropping and getting those basil plants out of the greenhouse and starting anew. I just think that's fundamentally a better production approach because of the insurance that you have. And we're really limited with controlled environment food crops with how we can control pests. And so prevention is really the best way. So I just fundamentally am biased towards a single harvest. But people will get a second harvest out of their crop.
Does that is there like a higher does it grow? Is the mass production like faster?
I can't answer that question. The texture and the flavor will change on second cut crops. They tend to flower quicker on that second cut. And generally when a basil starts to induce flowering, it'll start to upregulate some of the production of those compounds, but it can get to the point of being too much. And where on our linear models with blue light is too much, I can't answer that question. So some people will prefer a spicier basil, but if it's in a flower earlier, you get less leaves formed before that flower. So in a way, your yields might go down even further, as opposed to planting a younger plant that's farther away from initiating flowers. Yes?
So in regards to light and temperature, have you looked at, are the similar, like, crops that are grown in similar temperatures, do they also grow under the similar light constraints?
That's a good question. Right now, now that my tenure decision is done, I get to revise all my old data, and now I get to start to write papers again. And so I'm actually bringing out all that old temperature data and starting to do the modeling on that. So the three moderate light crops were parsley, sage, and mint. And I can't recall, parsley is a moderate temperature crop with an optimal somewhere between 21 and 24 C, and it's also a moderate light plant. But you can't, whereas the other ones are high light plants, even though they're moderate temperature crops. So I don't know that I can completely answer that question yet. But Kelly Walters, that student that I mentioned, for her PhD, she's actually working on some interactions of light and temperature, and I think she's doing basil, parsley, and dill. I think those are her main three crops. So she might be able to talk a little bit more, or at least later this year when her work comes out, that might speak to those interactions more and see how they interact. Because we only did a single factor experiment.
I know some more questions came up in chat.
Oh, hi, Anna. How are you doing? She was an undergrad at, it might seem, okay.
Should repeat the question.
Okay, sorry. In economic, because it's not up there. Sorry, I'm pointing at it like you see it. How far saturated is the market for herbs like basil? It seems like some areas like the Twin Cities, there were tons of choices in the produce section for local hydroponic herbs. So this is what I'm going to tell you, Santa might not be real. One of the things that happens with herbs is it's often very common to resell herbs, where producers will bring in boxes of field-grown basil from Hawaii, and then they'll repackage it in their packaging. So as far as whether they're locally grown, like like Anna was talking about in the Twin Cities, I can't answer that if it's saturated, because I know for sure, I know of one local Twin Cities grower who shall remain nameless, should say grower, that's repackaging field-grown basil as their own product. They're not saying that it's locally grown, they're saying they're a local company, but they're passing it off as local basil. And I know that at least one of our producers in Iowa, it was like when I saw the price tag on my Christmas present, when I saw his field-grown basil. People are still bringing in field-grown crops and just marketing it under their clamshell when they have depressions in production, like in the winter, or some people are just doing it as a marketing scheme. And there's nothing wrong with reselling a product, but I think that it's not generally as forthcoming as if it was resold versus if it was grown in the state. So I can't answer that question. I do still think that there's an opportunity for local production, just based on the volume consumed. Yeah, Neil.
What's the second most popular herb behind basil?
Mint.
Oh,
You can thank the mojito for that.
right.
That's not a joke. I mean, it absolutely is. Mint is absolutely the second most popular herb, and a lot of that has to do with popular cocktails.
Okay, let's again thank Chris.
This has been a production of Cornell University, on the web at cornell.edu.